Hey guys, welcome to the next HNMR video. So this one we're going to talk about how we draw a structure based on the HNMR spectrum given. Alright, so this is a little bit tricky. A lot of people don't like this sort of thing, but you take it step by step, it's not going to be that bad. Okay? So before we even start this, I'm going to mention a couple of peaks that you guys should know, or a couple of certain areas that you should know for HNMR. Okay? This you could maybe put on your index card if you're not too sure about it, or just remember it, but you will be practicing with it. You'll see it a bunch of times because they're very common. They're very common peaks. Okay, and so one of the things that you guys should know is that if you have something from 6.5 to 8.5, right, or about 7 to 7.8, which is I'm getting these values straight from your cover sheet on the HNMR. So like about from here to like about here, that's indicative that you have a hydrogen on a benzene, or right, it's on a benzene. Also, remember, when you do CNMR, HNMR, and they give you a formula, one of the first things you need to do is calculate IHD, right? If you get an IHD of 4, most of the time that means you have a benzene ring. So always watch out for that, okay? Usually means that you have a benzene ring. One of the other things that I'm going to mention is there's there's 3 HNMR patterns you guys should know that'll help you out. So if I had this ethyl group, right, so we have right here, the way that the HNMR pattern is going to look like is something like this. You're going to have a quartet, you're going to have a triplet. And where are these coming from? Remember, there's 2 hydrogens here. Oh, let me change the color on that. 2 hydrogens here. And 3 from that methyl. N+1 rule. 1, remember, accounts for that one, or the group. It's looking at 3 hydrogens adjacent to it. That's 1 plus 3, 4. This triplet right here is going to count from these hydrogens. It's looking at 2 hydrogens from these 2 red ones. 2 plus 1 is 3. Now, the one thing you guys need to be careful about is, depending on what this R group is, we can have different splitting for this guy, okay? Because right now it's a triplet, it's a quartet, because there's only 3 hydrogens here. If there was another carbon with more hydrogens, we can get more lines, okay, more splitting, okay? That's the ethyl. Now there's an isopropyl split, which looks like this. This is the isopropyl. So those 2 methyls, remember, they're exactly the same. So the HNMR is only going to pick up one of the hydrogens here. I'll actually draw the hydrogens out. Here's the carbon. They're all bound exactly to the same carbon, bound to that middle carbon right there. So they're considered the same. So all 6 of them are identical. So there's going to be one signal for them. And the other hydrogen that we have to look at is that one right there. So let's do the splitting pattern for the red ones first. Remember the N+1 rule. Let's just look at this one hydrogen. It's looking at that one blue hydrogen, that's the one adjacent to it, plus 1. That's going to give us 2. Right? So 1 plus 1, that's 2. That's going to give you a doublet. Okay? And then this blue hydrogen, it's looking at 1, 2, 3, 4, 5, 6, plus 1 is 7. Now, it's going to be very difficult to see 7 peaks. What we call that is a multiplet. It's going to look like something like 1, 2, 3, 4, 5, 6, 7. They're going to be really clustered together, really small. So it's going to be like this. Sometimes you're going to have a hard time telling how many peaks there are. It's going to probably look like this on your HNMR. Or even more clustered together. Right? And then the last one you guys should really be familiar with is the tert-butyl. And again, based on what this R group is here, this H can have more splitting. Right? So it's going to be even harder. It could be even harder to see. we have this carbon with its hydrogens, this carbon with its hydrogens, this carbon with its hydrogens. So H, H, H. Now, remember, all of these hydrogens are unique. Look at the way that they're bound. I'm just focusing on this hydrogen. It's bound to a carbon with two hydrogens other than the one I'm looking at. That's bound to this carbon, bound to the R group. Now looking at this hydrogen, it's bound to this carbon, bound to this center carbon, bound to the R group. And same exact thing for that. So they're all identical, all 9 of these hydrogens. Okay? So all 9 of these hydrogens are identical. So there's only going to be one peak for them. So now let's do n+1 rule. There are no adjacent hydrogens here. Okay? None. So that's going to be 0 plus 1. You're going to get one peak. Okay? There's only one peak. It's a singlet. You'll have a straight line. Now, before again we get started, now this question doesn't show you it, but there is another aspect of HNMR that I did not go over called integration number. Oftentimes on a peak, you'll see something like, now, what I'm about to write is not going to be accurate for this question, but it's just for an example. So you'll see something like, next to your peak, you'll have 3, 2, and 1, right? What those numbers mean is that, again, they're called the integration number. They tell you the amount of hydrogens represented by that peak. So if I look at this terbutyl group right here, this singlet, remember, because only unique hydrogens show up, that singlet represents 9 hydrogens. So the integration number for that is 9. Looking at this one, we're going to get a doublet from those red hydrogens, right? They're looking at 1 hydrogen. So that's going to be 1 plus 1. That's going to be 2. But that accounts for these hydrogens. So it's going to have a doublet. And the integration number is going to be 6 because it accounts for 6 of those hydrogens. And this hydrogen right here is going to have an integration of 1 because there's only 1 it's accounting for. And for this one, we draw out the splitting pattern here, right? This is going to have an integration of 2H because here we go, right? We have these 2 hydrogens. And the methyl is going to have an integration pattern, an integration number of 3. Okay? They may not write 3H, they could just write 3. But just watch out for that. That's what integration means. Okay? So now let's get to the problem. Just erase this. So, we have C4H8O2. First thing you always have to do when doing HNMR, CNMR, always calculate your IHD. So again, that formula is going to be 2C plus 2 plus N minus H minus X. That means halogens all over 2. Okay? So we're going to have how many carbons? Let's see, we're going to have 4, right? So 2 times 4 is going to be 8 plus 2 plus 0 nitrogens minus 8 hydrogens minus 0 halogens over 2, right? 8 plus 2 is 10 minus 8 is 2 all over 2. That's just going to be 1. You have an IHD of 1. So a good thing to do when you have an IHD of 1 and you have oxygens is to draw a carbonyl like this. Start your entire structure based around the carbonyl. And here's the carbon here. Okay? Because chances are it will be that, so it will help you. Not always, right? But it's a safe bet to start out with. So that accounts for one of our oxygens and one of our carbons. So we're going to leave that for now. Now what we want to do is I want to analyze the HNMR peaks, right? That's the whole purpose of this. So let's see what we have here. You can see that we have 1, 2, 3, 4 lines there. That's a quartet, right? Now remember, the n+1 rule tells us the splitting. So we have n plus 1 equals 4. That tells us how that's going to end up on the graph, which is the 4, right? This right here. So what we need to do now is to then tell the amount of hydrogens adjacent to that. We can just subtract 1 and equals 3. So whatever this peak is representing, this group right here, whatever that hydrogen is, it's looking at 3 hydrogens next to it. Okay? So keep that in the back of your head. It's looking at 3 hydrogens next to it. Now let's look at this peak right here. So it's a single line, and again, they're not giving an integration number here, which would make it a little bit easier. So it's a single line. So n plus 1, it's going to be 1. Subtract the 1, you're going to get n equals 0. That means whatever the hydrogen is that we're looking at for that peak does not have any hydrogens next to it. So no adjacent H's. Okay? Now, this is the last peak. We have 1, 2, 3. That's a triplet. N plus 1 equals 3. Subtract 1, you're going to get 2. That means whatever hydrogens we're looking at, so whatever hydrogen we're looking at, next to it, there are 2 of them. Okay? So let's go back to the carbonyl. All right? So we're going to have to build it off base of that to make it easier. I'm going to move it over a little bit. Oh, never mind. All right, so here's our carbonyl. So the easiest peak to probably start out with is this singlet. It says there are no adjacent hydrogens next to it, right? Again, whatever hydrogens we're looking at for this peak, there are none next to it. Now, you can see right here, carbonyls, remember, this one does not have a hydrogen on it as of yet. We didn't put anything here. So if I put a methyl right here, there are no hydrogens coming off of this carbon, right? So here's the 1 hydrogen, 2 hydrogen, 3 hydrogen. So we're going to be looking at one of them. So n plus 1, right? There are no adjacent hydrogens on that carbon. So n plus 1, we're going to get 0 for n, plus the 1, that's going to be a singlet, 1. So that makes sense for our singlet over here. Okay, the methyl off of the carbonyl carbon. All right, that's so far 2 of our carbons down. We just have 2 more carbons and 1 more oxygen. The hydrogens will fall in place pretty easily. You don't have to worry about them like that. So now what do we have to do? So it says that we're going to have a quartet and a triplet. That's what's left. If you remember the splitting pattern I told you guys about, an ethyl group represents that exact splitting. You can get a quartet and you can get a triplet. So let's say I draw this ethyl here. Here are the 2 hydrogens on that carbon. Let's pick these a different color. Here are the 3 on that one. Let's see if the splitting pattern makes sense, right? So we're looking at these. Oh, let's change that. Remember that those 2 blue hydrogens are identical to each other, right? So we're going to be looking at them as 1, like we've done for all the splitting patterns. We're going to do n plus 1. There are no adjacent hydrogens here to worry about, just the green ones, which means that it's going to be 3 plus 1 is going to be 4. That's where our quartet comes from. Okay, so looking at that, we got a quartet, makes sense. What about the green? If you look at the green, remember we treat them all as 1. They're identical. The amount of adjacent hydrogens it has are these 2, right? So let's see, that's going to be n plus 1. So 2 for n plus the 1 is 3. That's the triplet. That makes sense. So that splitting pattern works. So let me just clear this stuff up. So the ethyl is what we're looking at. But we have one problem, right? Where's our other oxygen? Right? We still have 1 oxygen we didn't take care of. We have all 4 of our carbons. The last thing remaining is that oxygen. Where are we putting it? Well, we have to keep our splitting patterns the same. So if I'm going to add an OH, That's another hydrogen that can be showing up in this peak in the HNMR. So that's going to be a problem. So we can't have an OH. So somehow we have to put an oxygen in their compound in which it doesn't have any hydrogens. One way we can do that is to have something like this, R to O, R, this ether, right? Therefore, it has no hydrogens. So we're going to have to put it in between carbons, right? So one way we could do that is this way. So we have this oxygen bound to the carbonyl carbon, and we get this ethyl group coming off the oxygen. Now let's see if the splitting pattern works. Nothing really happened to the hydrogens on this carbon, right? So N+1, there's still no adjacent hydrogens, so that's still going to be the singlet. What about the hydrogens here? And here are the other ones. So again, let's look at this. N+1 rule for the blue hydrogens, 3 over here. The oxygen has none, so it's still going to be 3 plus 1 quartet. Makes sense. Green hydrogens, they're going to have, again, we treat them all the same. They have 2 neighboring hydrogens. 2 plus 1 is 3. There's our triplet. Okay, so that makes a lot of sense. Now, here's another thing that we can help figure this out. You may be wondering, why is it that I put it there, the oxygen, but not here? Right? This way. Okay, what's that reasoning? Well, it has to do with the way that the HNMR, well, the positioning of our triplet. You can, sorry, not a triplet, the quartet. Look at where the quartet is. It's far to the left, right? That's going to be a lot of de-shielding. Where's that de-shielding coming from? So if you look at your exam 3 cover sheet and you look at the HNMR values, you'd see that they're going to give you, they wrote it as this, X, oh, let's change that color, X to CH. That's the H that we're talking about, where X equals an oxygen, a bromine, chlorine, or nitrogen. You're going to be approximately in the 3.3 to 4.0 range for HNMR. Right? We're right next to 4 for that triplet. It's right on it. So that implies that the oxygen is bound directly to that hydrogen with that's giving us with the carbon with the hydrogens that's giving us the quartet. If our methyl is bound to that oxygen, what's going to happen is the singlet and the quartet are going to swap places. So our HNMR is going to look a little bit like this. You're going to have here, that was really bad, and the straight line. So you're going to have your triplet, right? You're going to have your quartet, and then here's your singlet, which would have been around 4. Okay, so that's how we know that the oxygen should be placed here, connected to that ethyl group versus the methyl, right? So that's how we go through HNMR problems. Next video, I'm going to go through another HNMR problem, combining CNMR, all right? Hope this video helped. I'll see you guys in the next one.